Hey. Hey guys, this is another video for you to work on some of the homework problems. This is for Unit 5, and the problems are 427, 445, and 453. So I sketched them up here to save us a little bit of time. Let's take a look at each one, make sure you get the basic idea, and then you should be able to handle them no problem. So first one, 427, has two different setups, and each one has two forces. It's very simple, just says, tell me what the net force is. There's not much to it. Well, we've already talked about net force quite a bit. And you know, if you want to get net force, F net, that is equal to the square root of the sum. Remember that little funky Greek E, or really it's a sigma. That means sum up or add up. So add up all the forces in the x direction, square that, and sum up all the forces in the y direction, square that. Now, if you look at that equation, it looks kind of like the Pythagorean theorem, because it is. You know, a net force, if I took the square on this side, would be F net squared equals sum of Fx squared plus sum of Fy squared, just like c squared equals a squared plus b squared. We're just making triangles. That's all we're doing. So if you look at this first example, you have two parts of the triangle. Now, the temptation would be just to connect these lines and say, well, hey, there's F net. But we don't add vectors that way. If you think way back, when we started talking about just displacements, when we first originally talked about vectors, we said you don't go for a trip and walk a mile east, then run back to where you started and go a mile south. You keep going from where you left off. So if I wanted to add these two up to get the net force, I would start going over, and then I would go down. So my result is start to finish. There is F net. Now if you look at it here, we have F net. This is Fx, and this is Fy. Now because there's only two forces in this problem, we don't need to do this big summation. You don't need to add them all up. If there were, say, 15 forces in this problem, we would do the same thing. We would just add them all until eventually you made a really big triangle. That's it. So you can put numbers in there, solve for it, but you'll end up getting that F net is going somewhere this way. Remember, this is, we're talking about static equilibrium now. So if I were to rewrite this problem, my question would be, what force would I have to add in order to put it in static equilibrium? So if you end up finding that F net is, say, 20 newtons, 13 degrees, in the negative y of negative x, then you would want to have the new force be up this way, go in the opposite direction. That would put it in static equilibrium. But it doesn't ask you for that, so you don't have to worry about it. Second problem is the exact same thing. The only added piece is that these are separated by an angle of 120 degrees. So it's not as simple as just adding fx and y's. And we have to get there first. So one of the things that we can do is take this force, F1, and break it into two pieces. So we can say, instead of thinking about this force at an angle, let's pretend that there's a force going straight down and a force going over. So we can have an F1 x component and an F1 y component. So now we have three total forces, F2, F1y, F1x. Well, in the x direction, there's only one, so that would just go in here and get squared. In the y direction, there's two, so we add them up. But you need to be careful when you add them up because they're going in opposite directions. F2 is in the positive y direction, F1y is in the negative y direction. So it's not going to be as simple as just add them up. You'll end up getting a really big number that's not correct if you do that. So next step is, how do we actually get these? Well, if this angle is 120 degrees, this angle here is 60 degrees. And if that's 60 degrees, I can use a little bit of trig to find F1x and F1y. F1x is across from the angle. The angle sees this, so I would have F1 times the sine of 60. F1y is next to the angle. It's with it. It's collaborating with it. So F1y equals F1 times the cosine of 60. I'll let you finish it from there. But again, just calculate net force and you're done. If I were to say add another force to put it in static equilibrium, you would say, well, it's got to have an x component to cancel that out. And then depending on which one of these is bigger, it'll either be over and a little bit up, over and a little bit down. If those two were exactly equal, it would just be straight over. But in this case, your net force is probably going to be somewhere in this direction. Okay, that's the first problem. Done. Let's look at the next one. You are applying a 730 Newton force to two blocks that are side by side. Now, don't make this needlessly complicated. Two blocks that are side by side that are basically attached, we can just treat as one block for the time being. So instead of saying it's two and you're going to think of it separately, draw a little box around it in your head and say that one box is actually 185 kilograms. So now I have a force and a mass. Not bad. If there was no such thing as friction, you could calculate the acceleration, no problem. It would be very easy. But there is such thing as friction. Now, we will, if we haven't already, talk about friction in class. But the force of friction depends on two things. I know we already did this. We already talked about those two things it depends on. One is how hard are two surfaces being pushed together. You know, there's no friction between my hands right now because they're not even in contact. And now there's a little bit because they're gently being pushed together. Now there's a lot of friction because I'm pushing them together hard. So one factor that affects friction is how hard am I pushing into the surface? Or really, how hard is the surface pushing against me? And we've talked about that concept before. We call that normal force. How hard a surface is pushing against me. Well, the other thing that we talked about is texture. You know, your hands over millions and millions of years have, well, other creatures of millions and millions of years, 350,000 for us, but they've evolved to be sticky. That helps us hold things. If we happen to have Teflon-coated hands, life would be really difficult. We wouldn't be able to pick stuff up. So our hands have a very high coefficient of friction. You know, the texture creates a lot of friction. Other materials don't have a lot of friction. So we did the experiment class where you put your hand on the desk and slid it around. It was difficult. And you put your hand on a piece of paper and slid it around. And the paper in the desk slid no problem. So it's kind of hard to describe what makes a surface, you know, frictiony. It could be sticky, it could be rough, it could have like a stretchy material like rubber. So instead of trying to describe one aspect of the texture, like how rough it is, how sticky it is, how stretchy it is, instead we just use this kind of catch-all term called coefficient of friction, and we use the symbol mu for it. Looks kind of like a backwards U with a really long tail. So usually you'll be given a coefficient of friction, or you'll have to calculate it. I think in this problem it's given to you. But we want to figure out, well, I'm pushing this hard, how much is friction pushing back? And friction always resists motion. So if I'm pushing the blocks this way, friction's pushing back. If I try to push these same blocks that way, friction pushes back. So to figure out how much, you say, well, I need the coefficient of friction, which you should have, and the normal force. Well, remember these blocks are sitting on a tabletop. Gravity is pulling them into the tabletop, and normal force is pushing up. So a lot of times, not all the time, but a lot of times normal force is going to be equal and opposite force of gravity, which is mass times acceleration of gravity. So in this case, that total mass, 185 times 9.8, gives you about 1,600 newtons of normal force. So if I know that, and I know mu, I can figure out how much friction is pushing back. Great, but we're not done. So now that I figure out how much friction is pushing back, I can figure out kind of the net effect. So let's say, hypothetically speaking, if friction was pushing back 500 newtons, and I'm pushing forward 130 newtons, I'm going to have a net force, so I'm going to have an acceleration. Now if we have a 3x diagram here, and I say my F pushes this way, and force of friction is that way, but if my push was bigger than friction, I would end up having an F net that way. And we all know that F net makes a mass accelerate. Now, this is still the mass. The total mass, the whole thing. We're treating it like one box still. We haven't changed that. So, with that total mass, you'll find the actual acceleration for both blocks. Great. Now we got to go one last step further. Because if these two blocks are accelerating together, they'll stay in contact. But there's a force here. That first block is being pushed into the second one. If the second one wasn't there, and you're still pushing 730 newtons, this first one would accelerate a lot faster, or a lot greater. But because that second block's there, we're pushing into it, some of my effort goes into this second block. In fact, more than goes into the first, because it's more massive. So, how do I figure out how much that is? Well, if I know that I have an acceleration of a certain amount, all right, this accelerates at that rate, and this accelerates at that rate, doesn't it mean that this particular box has to have a force to make this particular mass accelerate at that rate? Yes, it does. So I can apply F equals ma again, F net equals ma again, but now, just like before I said that total force on the total mass, now to find out this individual force, I just use this individual mass. That should do that for that problem. So, let's look at the last one, this inclined plane problem. I'm going to cheat real quick and look at what it asks for again. Okay, in this one you have a block that is moving up a hill. It's already moving. It's got an initial velocity of 3 meters per second. It's going uphill. And it asks how far it's going to get before it stops, how quickly it will come back down. Well, remember I told you my anti-lean was great at these problems. So what we're going to do is first we're going to diagram it, and then I'm going to do it my anti-lean way. So what's really affecting this mass? Well, one thing only, gravity. And gravity goes down. Fg. But down is not a convenient direction for this problem. I mean, we're working on an angle. It would be really convenient if I knew how much of gravity was pushing the block down the hill. We all know things roll down hills. They roll down hills because of gravity, but gravity pulls straight down, not over. Well, how can that be? Well, gravity is a vector, or force of gravity is a vector, and like all vectors, it can be broken down to components. If I have a force go in this direction, I can break it down into an x and a y. Well, that's true no matter what direction that force is pointing. It's just that if I'm at a weird angle, these are no longer x and y, they're going a different direction. So what? We pick x and y because normally it's very convenient. In this problem, it's not. So let's not break down gravity into x and y. Let's break it into convenient directions, like the parallel and then the perpendicular. So I'm going to draw a parallel line. Well, I'll do the perpendicular first. I'm going to draw a perpendicular line. And now I'm going to draw a parallel line and make my triangle. Note that the 90-degree angle is here. That has to be parallel. If you come down here and draw your triangle this way, you have two problems. One problem is that this line is not parallel with that line. The other problem is now you've made this the hypotenuse of the triangle. When you're breaking down a vector, the original or the actual force, the actual vector, should be the hypotenuse. We're breaking it down into smaller parts. You can't break it down into a bigger part. That makes no sense. So let's just get that out of here so we don't even get tempted to put it in. So we're going to say, we have a force perpendicular, a perpendicular component of gravity, and we have a parallel component of gravity. And we can get those with trig. We just need to know what this angle is. And if we do a little teeny tiny bit of geometry, we can say, here's a right triangle, this triangle here, and that's 22 degrees. So if this is 90 as a whole, then this side is 90 minus 22, which means that side is 90 minus 90 minus 22, otherwise known as 22. This angle and this angle are always the same. Very convenient. So there's 22 degrees. Well, if I know that angle, this is across from it, I can get F parallel is equal to FG times the sine of 22. Now I know my parallel force. So we can kind of draw this again if we wanted to, and say that I only have this block that is being pulled this way, because we're not really going to care about the perpendicular force. Since there's a normal force from the ramp that's pushing back, they cancel each other out, doesn't mean anything. And there's no friction in the problem, because if there was normal force and a coefficient of friction, we'd have to worry about that. Luckily we don't. Alright, so we're only worrying about this parallel force. The block was originally going that way, there's a force pulling it back. Now it's just a simple motion problem. I'm going to move the computer because you're not going to be able to see anything else. But real quick, let's look at this like my Aunt Eileen would. So there's the problem. Ooh. There's the problem as we see it in our book. Here's the way that my Aunt Eileen sees it. This is awkward trying to do it backwards. It's a flat surface. Alright, gravity's pulling at a weird angle. So we say, oh, I got it broken down to my x, and my y. Now, we're going to draw it again. There we go. Alright, so, but now let's turn our heads. We'll draw it just like my Aunt Eileen would. Here's the object. And gravity was pulling at an angle. We broke it down into a perpendicular and parallel force, so there's a parallel force going backwards. And that's it. It's the only thing we're worried about. So that means there's going to be an acceleration this way. F parallel is going to make this mass accelerate. So there's an acceleration that way. There was a velocity this way. Well, how long is it going to take to stop? It's a simple acceleration problem. A equals delta V over t. Our final velocity we're concerned about is 0. Our original is 3. Can you find the time? Sure. Well, how about how far it went? Don't worry about having a delta x parallel or a delta whatever symbol for that direction. Turn it in your head, and now you have a delta x problem. Equals VO times t plus 1/2 AT squared. Just keep in mind that VO is that direction and A is this direction. So they should be opposite signs. That should get you for all these problems. Hope that this helped. Bye now.